right, so let's see how you're doing on that. So give that one a try. Can you take 36 and change it into a base 2 number? Hey, in base 2, what's the biggest digit we're going to see?
42.
What's the biggest digit in a single spot we're going to see?
1.
1, yeah. In base 2, you're never going to see a 2 or bigger, huh? Remember how that works? So it's all going to be what? Zeros and ones. What do we call that? What do computer people call that? Binary. 0, 1. That's how computers communicate. Circuit on, circuit off. 0, 1. We're going to see how computers work. How can they communicate things? So base 2. Remember the base 2's on the side? So you put the base 2 stuff. It doesn't say 2 right here on the 36, huh? So that would be when I put the base 2 stuff right on the 36. It's over on the side. So I'll put the base 2 over here on the side. So you start with a 1. Remember, you always start with a ones place. And then you just go times 2, times 2, times 2. How far do we go?
32.
Yeah, you go until you're bigger than the number, then back up, huh? So yeah, 1632 is going to be where we start. Because if you do another one, that's 64 and that's too big, right? That's bigger than our original 36. So you want to start at the biggest place value that's not bigger than your number. So 32, huh? We good there? Remember that? So, okay, so we start with the 32. And then we just long divide, don't we? We say, how many times does 32 go into 36?
Once.
Well, once, huh? Yeah, one time. And that leaves 4 left over. So this is 132. And that leaves 4 remaining. This is the remainder. 4. So what do we do now? So we're trying to, with these ones and zeros here, right? Because we're on base 2, you're never going to see a 2, so ones and zeros. So with ones and zeros, we're trying to represent 36, the number 36. So a 1 here means 32. So we have 4 left to represent. So what am I going to do? Can I just jump to the answer? And don't I just need 1 in the 4's place and zeros everywhere else? And that's it. Because that's got to be 36, doesn't it? Does that make sense? Because that's 32, 1, 32, and 1, 4. Base 2 is kind of nice that way. It's just 1 or none, you know? So that is the number 36. I mean, you could have gone through the formalities if that bugs you when I changed up sort of the plan. If you wanted to be formal about it, normally what you would do next is you would go, okay, I got 4 left, and then I'm supposed to try to divide 16 into 4. Right? Remember, these numbers go on the outside. Like the 32 went on the outside. And that would go in 0 times. Right? And then you'd have remainder of 4. So there'd be a 0 there. Then you'd try to go 8 into 4. See how it's kind of a waste of time, really. It's just going to keep being 0. Just in the end, you need 4 more. 32 and 4 makes 36. That is the number 36 in base 2. Does that make sense? So 100,100 base 2 is 36. How are we doing? So I want to give you kind of a weird one. Base 2 is a weird one. So do you see how this is how computers work? This is how stuff inside of a circuit board communicates. Like, how do computers know letters and all that kind of stuff? Well, it's exactly this, because in the end, computers are just wires, aren't they? They're just wires, and there's either electricity in a wire or not. 1 or 0. It's binary. That's the language of computers. When people say computers' internal language is binary, what they mean is anytime you type something on a computer, Joe ran down the street or something, you put it. The way the computer stores it is a bunch of 1s and 0s, meaning, for example, it has the alphabet. So, it has like A is 1, B is 2, C is 3, D is 4, E is 5, etc. And so how does it represent the number 3? All it has is wires. Well, how would you represent 3 in base 2? 1's place, 2's place, 4's place. How do you do the number 3? 1, 2, and 1, 1, huh? That would be the number 3. 0, 1, 1. Make sense how that's the number 3? So that is a 3, so that could be the letter C. Does that make sense? How a computer would store that with just wires? It's binary. So when we say like a 32-bit processor or something like that, that has to do with how many different places it has wires that communicate 0s and 1s. So the more it has, the bigger the numbers it can communicate and store and act on. It's all ones and zeros. But with ones and zeros, you can make up any number, and you can translate those numbers into letters, and you can make words, and you can store anything, all in ones and zeros. See how it works? So anyway, we're not doing a computer class, but I thought that was a nice tie in there. So yeah, so we good on that? Any questions on converting? Want to try one more on this? Like maybe a more regular one. Like, yeah, let's do the, how about 404 into base 4? We'll kind of go backwards here. So how about number 4, which says 404 into base 4. Let's try that one. 404 into base 4. So try that one. All right, so again, base 4, do that on the side. Start with 1, go times 4, times 4, times 4. Use your calculator. 256. Next will be 5,024. That's too big. So we start at 256, right? Remember, so you want to go beyond the number. So I just kept multiplying by 4 until I was beyond the number. Cross that one out. So we start with 256. And then we just long divide. We say, how many 256s do I need to represent the number 404? We're trying to make 404 out of those pieces, aren't we? So how many 256s do you need? Well, let's check it out. 256 goes into 404 just one time, huh? One time, and then subtract, I don't know, 148, all right? 148, so that's the remainder. So if I put a 1 here, because of that 1, so I've got 148 remaining to be represented. So now we go, okay, 64 into the 148. Is that twice? Twice, I think. Yeah, it'd be 128. Subtract 20 remaining. So that's 2 here. And now we have 20 remaining. So then you go 16 into 21 time. So 1 and 4 remaining. So that's easy. 4 and no more. Good? Now that makes sense. So 12110 base 4 is the same as 404. Good? Questions on that? We all good? All right. So you see the difference? 1011 base 2. 1011 base 2. So I'm not going to put the base 2 place values on the side. I'm not going to go over here and go 1, 2, 4, etc. because the 2's right on the number. That means this number itself is a foreign number. It's got the subscripts right on it. So that means this is the 1's. Let me do a different color. This is the 1's place, 2's place, 4's place, 8's place, etc. Right there on that number. That is the foreign number rather than putting the foreign number on the side. Everybody see the difference? So back here, the 404 was a normal number because it didn't have a foreign subscript. They wanted me to change it into a foreign number. This one is a foreign number. It's right there. So what does that mean? It's 1, 8, no 4s, 1, 2, and 1, 1. 1 times 8, 1 times 2, 1 times 1, what is that? 8, 2, 1. That's the number 11. Good? You good with both those directions, forward and backwards, changing into and out of foreign language system? How about number 11 there? What's the greatest 3-digit number you're going to ever see in base 6? 555. Yeah. Well, in base 6, you're never going to see a 6. So the biggest thing you're going to see is 5. So the biggest 3-digit number is 555. Base 3. That's not 555, but yeah, anyway. And then what's the biggest number you're going to see in base 3? Yeah, this is easy, huh? What's the biggest thing you're going to see in base 11? Yeah, 10, 10, 10, but we do TTT. Yeah. Good? Those were easy. That's homework number 2. It's hardly anything new. It's basically just a review of homework number 1.